Welcome, this is Jianying. I'm Associate Professor in the Faculty of Electrical Engineering, Mathematics, and Computer Science at Delft University of Technology. The topic of this lecture is DC motors, and we will discover the structure, principle, and models of DC motors. The outline of the lecture is as follows. We will start with the structure of the DC motor and its operation principle. After that, the equivalent circuit is introduced and the steady-state performance calculation will be studied based on it. By the end of this lecture, we will also introduce the dynamic model of the DC motor, which is essential for our follow-up studies on DC motor control. So, how to construct a DC motor? The figure on the top left shows the breakdown of a practical DC motor. The field winding on the stator is the source of the magnetic field, while the magnetic cores on the stator and on the rotor provide the paths for the magnetic field to flow through. The armature winding fixed in the slots of the rotor allows conductors to bear the current to produce the torque by interacting with the magnetic field. The brush commutators ensure the correct current flow direction by flipping the current in the armature winding conductor when it moves from one pole to another. This procedure is also called mechanical rectification. The animation on the top right shows how it is done. All conductors and the North Pole have current flowing into the screen, while all the conductors and the South Pole have current flowing out of the screen. This makes sure all resulted torques and different poles will have the same direction. Let's move on and see how exactly the magnetic field is produced by the field winding. By applying the Ampere's law, we can see that if the number of turns of field winding per pole is N and the field current is Rf, with an air gap length G between the stator and the rotor, the magnetic flux density magnitude in the radial direction in the air gap would be given by this equation, where μ0 is the permeability of the vacuum, so ideally speaking, the radial air gap flux density waveform would be a square waveform. However, the real world is never ideal in practice, because there is space between adjacent poles, that is to say, the interpole region, the air gap flux density waveform will deviate from a square wave as shown in the figure on the bottom. Once the magnetic field is generated, let's see how it is used to create induced voltage and force in the armature winding. To simplify the analysis, it is better to choose one single wire loop as shown on the slide. The wire loop has a width the same as the diameter of the rotor, which is 2 times r, and a length of L. Its two terminals are marked with the symbols A and B and are connected to two commutator pieces which are isolated from each other. As the rotor rotates around the axis, commutator pieces will alternatively be conducted with brush 1 or 2. If the rotor rotational angular speed is omega, the induced voltage on the side of the wire loop will be given by Faraday's law. Apparently, the induced voltage in each wire side will be alternating between positive and negative. So is the force applied on each wire side. However, because of the mechanical rectification of the commutator brush mechanism, when we measure from the brushes 1 and 2, only unidirectional voltage is measured. This is because the wire terminal connected to the brush alternates as rotor rotates. Based on the same principle, the torque applied on the wire loop will also be unidirectional, since the force on both sides is opposite to each other. In practice, the armature winding of the DC motor always has more than one wire loop. An example is shown on the left of the screen. In this example, all wire loops are lapped on each other. Thus, it is called a lap winding. To characterize the armature winding, we define the number of conductors exposed to each pole as Ca and the parallel path as M. then the induced voltage or back EMF in each conductor is given by BR times I times omega times R. The torque is derived from Lorentz force as BR times I times IA times R, where IA is the current in the armature conductor. The total induced voltage in the armature winding and the total torque on the rotor can be calculated by summing up those for each conductor as shown on the screen. Here we notice that, well, Ca, M, I, and R are all geometrical parameters of the motor, but BR is linearly related to the field current IF. If we synthesize all the geometrical factors as a mechanical constant G, two beautiful equations are derived from the induced back EMF and the torque. Obviously, the induced voltage is linearly proportional to the rotational speed omega, and the torque is linearly proportional to the armature current IA, while both are proportional to the field current IF. The next question is how to calculate the steady-state performance of a DC motor. The answer is to use the equivalent circuit of the DC motor, which is shown on the screen. It consists of two subcircuits, the armature circuit on the left and the field circuit on the right. From the last slide, we know already the equations of the back EMF and the torque, which are functions of armature current and field current. The armature current is related to the voltage supplied to the armature VA and the back EMF by applying Kirchhoff's voltage law to the armature circuit. Here, IA is the resistance of the armature winding. Based on the voltage equation, the armature current can be solved as shown on the screen. The mechanical power output then can be calculated in two ways, by multiplying the torque and the rotational angular speed omega, or by multiplying the back EMF and the armature current. The two methods lead to the same result, implying the conservation of energy. The previous DC motor example is based on the magnetic field generated from the field winding governed by Ampere's law. Here is another way to provide the magnetic field without involving the field current. The alternative way to produce the magnetic field is to use permanent magnets directly on the stator of the DC motor. This will lead to a new type of DC motor, the permanent magnet DC motor. Now, the stator consists of magnetic core and the point magnets. Since the point magnets provide magnetic field directly without involving field winding and field current, the loss on the stator side is reduced. The rotor structure is the same as the winding-excited DC motor, which consists of the armature winding, the commutator, the brushes, and of course the rotor magnetic core. The equivalent circuit can still be applied for performance calculation of the point magnet DC machine. However, we only need to study the armature circuit because of the elimination of the field winding. The field current also disappears from the back EMF and the torque equations, so that the back EMF EB and the torque TE are related to the angular rotational speed omega and the armature current respectively, just by a machine constant K. The equivalent circuit tells us the steady-state performance of the DC motor. However, for the control purpose, we would need the dynamic model of DC motors, which models the transient behavior of the DC motors when there are changes in either current or speed. Like any other dynamic systems, the dynamics of DC motor can be described by ordinary differential equations and corresponding block diagrams. To consider the electrical dynamics of the DC machine, the inductance LA in the armature circuit has to be considered. The voltage equation should be modified from the steady-state model by adding the item of ILA times the time differential of the armature current. This voltage equation describes electrical dynamics. However, a DC motor is an electromechanical system. We still need to describe its mechanical dynamics. It can be done by using the torque equation and by applying Newton's law to the rotor. Here, T is the torque output from the motor, TL is the load torque, J is the moment of inertia of the system, and B is the damping coefficient. The electrical and the mechanical dynamic equations are coupled to each other by the back EMF, since it is related to the rotational speed omega. The ordinary differential equations can be converted into a transfer function-based block diagram using Laplace transformation. Here, the block diagram is provided directly without further elaboration. In Module 5 of this course, you will learn it in detail for controller design. Looking back, we can see that the DC motor has linear torque and back EMF characteristics, which is advantageous for motor control. Its steady-state performance can be analyzed by equivalent circuit and applying Kirchhoff's law, and its dynamics are modeled by differential equations or transfer functions. Hereby, we conclude the lecture. Thank you for watching this video. Good luck with the rest of the study.